I just want to look at a couple of different problems that have appeared over the past few years, that some that look incredibly difficult and some that are maybe incredibly difficult depending on how you look at them. But remember, these are HSC, so this is like endpoint. So in 12 months' time, the sort of problems that you'll look at and go, yeah, I can do that. Right now, you might look at it and go, oh, I'm never going to be able to do that. But we'll see. So this one came in 2006, and they gave you a bit of a hint, first of all. We've got a trigger relationship to prove here. So they told me to use the fact that tan alpha minus beta is that expression there. So obviously our regular formula. So I'm sort of looking at what we have to prove and thinking, well, how on earth does that tie in? And I'm seeing some similarities there. I can see a tan minus tan. I can see a 1 plus tan tan. So it sort of seems logical to make alpha equal to n plus 1 theta and make beta equal to n theta. Let's substitute it into the formula that they've given us the hint about. Let's see what happens. So we get tan of n plus 1 theta minus n theta is equal to tan minus tan on 1 plus tan tan. Now n plus 1 theta minus n theta, that's just theta. Okay, so I've now got tan theta is equal to that. So let's have a look at what we're trying to prove. I guess what's standing out to me now is that on the left-hand side I've got 1 plus tan n theta, 1 plus tan tan, and on the bottom here I've got 1 plus tan tan. So if I was to multiply by tan tan and also divide by tan theta, it'll start looking like one. I said, and also divide by tan theta. Thank you. Okay, now let's compare that. Pretty close. But they've written, instead of writing it as over tan theta, they want cot theta, but of course the reciprocal of tan is cot. So we can do that. All right, so there's part I. Just a couple of comments there to let you know what happened that particular year. The comment from the examiners was, this part was not done well. Many candidates presenting circular arguments. So that's usually when you end up with things like 0 equals 0 and things like you multiply by something and then you divide it again and you're back to where you start from, and that sort of thing. So it was, and let's just, I'll click back again. So I guess it was a matter of looking at it and picking up the relationships. What's the same and so on. But a lot of people struggled that year doing that. I'm not sure how many marks that was worth, but so obviously if you get that one out straight away, you're a couple of marks or 1 mark ahead of everyone else. However, a number did successfully rearrange the given fact and did easily see the substitution that they had to use. I was only with 1 mark. Many candidates spent considerable time on this part, which was only with 1 mark. I guess when you're in an exam, whilst it's tempting to persevere and go, I'm going to get it, if it's only worth 1 mark, and they've given you the relationship that you can use in the next parts, sometimes it's better to go, look, I'll just come back to this if I've got time, let's move on. And because also, remember, sometimes when you come back with a fresh mind after you see it straight away. You might look at something for a couple of minutes and go, oh, I got no idea, but then you come back to it later and go, oh, of course, what was I thinking? Yeah. Use induction. So here's our induction. It is a series type. So tan theta, tan 2 theta, tan 2 theta, tan 3 theta, and so on. So, all right, let's prove it for the first case. And strangely, I've actually started with the right-hand side rather than the left-hand side this time. So on the right-hand side, when n equals 1, I get negative 2 plus cot theta tan 2 theta. All right, left-hand side, obviously the first term there's tan theta, tan 2 theta. I want to show these two things are the same. Well, it's got to tie in, you would think, with what they just asked us to prove. And what they just asked us to prove was not that tan tan equals something, but 1 plus tan tan equals something. So I'll make it 1 plus tan tan, but then of course I've got to subtract 1 as well. And then I can substitute in what we just proved. So I'll get cot theta tan 2 theta minus tan theta minus 1. Okay, we've got to get to minus 2 plus cot theta. Well, I've got the cot theta times the tan 2 theta. Of course, cot times tan is 1. So we get minus 1, there's our minus 2. So that was just proving it true for the first case. So you can imagine that particular year when people got this induction and they go, that's just n equals 1, now I've got to do the actual proof. Well, my God. Okay, so I'm going to assume it's true for k. So there's my assumption. Prove it true for k plus 1. So that is what we're going to attempt to prove. But it is a series type, so I'll do it the same way I always do series type. I'll rewrite it so I've got the sum of k and then add the next term, because then I can substitute in my assumption, which is minus k plus 1 plus cot theta tan k plus 1 theta plus tan k plus 1 theta tan k plus 2 theta. Can you see what I've done? I've used that tan-tan relationship again. See the tan-tan at the end? So I've got the cot times the tan minus tan, but of course minus 1, because the actual thing we were proving was 1 plus. That's going to allow me to tidy up a little bit, because if you notice now, I've got a plus cot theta tan k plus 1, but when I expand out this one, I'll get a minus cot theta. So that's going to eliminate those two terms. And I've also said, well, minus k plus 1 minus 1 gets me the minus k plus 2 that we're looking for. So I've ended up with minus k plus 2 plus cot theta tan k plus 2 theta. Where are we trying to head? Is that? Yeah, that's what you want. That's it? Brilliant. So bang, it falls out. So yeah, a little bit tricky, the manipulation, but we get there with only a few steps. Yeah, we get there. And the rest of it, of course, is just simply, oh, well, it's true for the first case, and so I can induce for all the others. So what did our examiners say about the induction? Most attempted it. It seems to imply that some didn't. However, many only earned the mark for stating the inductive step. They could not prove the expression true for n equals 1, as they couldn't link it back to part I. And again, you've got to think logically, why did they ask me to do part I? It must come into it somewhere. So you've got to be thinking. Consequently, of course, they couldn't then go and prove. Notice, it wasn't proving the inductive, it was simply stating what they wanted to prove, because they weren't actually able to prove the inductive part. Okay, let's have a look at this one from 2004. This one is sort of a series one, but instead of adding, it's multiplying terms together. But we can still use the same idea. So the first case in this one is, oh look, I did use greater than or equal to. So the first case is 3. First case is 3. Left-hand side, the first term would be 1 minus 2/3, which is a third. Right-hand side, 2 on 3 times, yes, that's a third as well. So that works out. Left-hand side, same as right-hand side. Okay, so I'm going to assume it true. So let's make n equals k. We want to prove k plus 1. Okay. Well, I will start it the same way, but instead of plus, it's multiply. I'll rewrite it as the multiplication of the k terms times the k plus 1th term. Sub in for the assumption. Now let's play. We got to get 2 on k plus 1 on k. Well, if I'm multiplying fractions together, it would make sense to make that second term one complete fraction. So, yeah, I assume that's what I did. So we got k plus 1 minus 2, which is k minus 1. Oh, it drops out quite nicely, doesn't it? Because now the k minus 1s just cancel, and we've got our result. But see, that sort of question would have thrown people, because it's not going plus, and that's what we're used to seeing. We're used to seeing plus. Oh my gosh, it's multiplied. What do I do now? And I guess that's what I was saying to you when we first started looking at this, is don't think of rote learning a solution and go, oh, series type, we always do sum to k. No, it's an idea. It's the idea that we're using. So yes, it's true for k plus 1 if it's also true for k. And etc, etc, etc. Mind you, that time I did go n is greater than 2 rather than going greater than or equal to. No. So what did the examiners say that one? Many submitted excellent excellent responses, including all the necessary components of the induction proof. However, weaker ones did not verify n equals 3. You would assume in the weaker ones they just out of habit went, oh, let's go prove it for n equals 1, rather than trying any. And of course you can't do it because it doesn't work. Had an incorrect statement for the assumption. That kind of makes it hard to prove if you got the assumption wrong. Or an incorrect use of the assumption. Not working out how to... Because I would imagine that incorrect use of the assumption was going back to, oh, it's going to be the assumption plus the k plus 1th term. But in this case, of course, it's multiply, not plus. Yes, if your algebra is not up to scratch, that would have been a bit tricky with that one, because we had to create the algebraic fraction and so on. Oh, well, that's what I was just saying, wasn't it? The rote learning of that idea caused a problem, thus making completion of the proof impossible. All right.